We're ready to go. So Riemann, of course, we all know, was a kind of universal genius, as Michael likes to say, slim volume of collected works. Each chapter changed everything in its different fields. So Paddy has a lot of interests. One of them is very much Riemann. I think he's written a book on the Riemann hypothesis.
Well, the Riemann zeta function.
Riemann and zeta function, I'm sorry, but let's start. But also he is the keeper, still is, but the keeper of the Riemann Nachlass.
Well, no, that's the SUB, but it is in Goettingen.
But it is in Goettingen, you are very familiar with what's in
yes,
there.
And
that's very important. There's a direct connection between Riemann's papers and Paddy. Paddy has looked at them in the flesh.
Yes.
And the audience today is also a reflection of Riemann, because we have mathematicians, physicists, and particularly some physicists who know about acoustics, so beware. Okay, I'm delighted with Paddy, who I think, this is almost the last of the topology seminars ever, as far as I'm concerned. And I think Paddy actually holds the record as the largest number of topology seminars. Not being a topologist is quite a trick.
It is quite an achievement.
Congratulations. Okay, there's Paddy. Going to talk to us about Riemann hypothesis. Gold at the end of the race.
Okay, well, thank you very much indeed. I have one or two things to say in advance. First of all, I spoke here about 18 months ago, and although this talk is not about topology in a direct sense, the last talk that I gave was about the history of topology, and this is in a sense in the same line of thought. Andrew had asked me to talk about Riemann in the context of Goettingen and the origins of his work on surfaces. And I became more and more convinced that in order to understand Riemann properly, one actually has to understand the context in which Riemann was working, who he was reading, and what else was going on. And for example, I will come back to this later on, the role, for example, of Johann Benedict Listing is extremely important and usually overseen by historians. This will come up again in the course of the talk. I should say that Andrew, this is the last talk, so I don't have to worry about being blacklisted, but I may overrun a bit. Andrew suggested that I sort of a little bit after 5, I stop for those of you who want to sneak out and have a break and then continue beyond that. So I will try and do this. I try not that it will not be excessively long, but I'm trying to do 3 separate things in this talk, and it's getting to be a bit too many things were put into it. Let me see if I can get this thing to work here. So
We have to point it at.
Ah, there we go.
No, you're not supposed to have to point it at it. I mean, it's supposed to work. So one thing is that at the very beginning, when I gave the title of the talk, there was one thing that had struck me very forcibly, which led to the business about rainbows being in the title of the talk. And I realized afterwards that this might lead people to false expectations of what I meant by the pot of gold and so forth. So I am not involved in trying to prove the Riemann hypothesis. I've never seriously been involved in trying to do that. On the other hand, I have been involved in finding out why other people's proofs don't work. And so I have been involved in that. And then I was involved. I was originally involved in this because of a talk which I actually attended in Paris by Matsumoto, who I admire enormously, who came to approve the Riemann hypothesis, and I put quite a lot of work into understanding why he hadn't. And then
Does
last
he
year...
admire you as much as you admire him?
What?
Does he admire you as much as you admire him?
Probably not. But we won't go into the details of this. And then there was a most peculiar event which I actually also attended last year in Belfast. Colin Reid gave this talk on the Riemann hypothesis in a pub in Belfast, sort of 1st of March 2015, so just over a year ago. It was a Sunday, so he clearly saw Marcus du Sautoy's TV program about the music of the primes, and I was there, and I was surprised at just how popular the talk was, and so I've offered to give a talk in a slightly different context, but in Belfast in about 3 weeks' time. And one of the problems that I'm talking about in this talk is the problem, how do you explain the Riemann hypothesis to those who are not mathematicians? And it has gained us an enormous degree of notoriety or fame or whatever, that the number of people interested in it is very, very large indeed. Riemann's paper on the Riemann hypothesis is probably the most famous single paper anywhere, ever. And not quite sure whether justly, but this is the case. And so this was one of the stimuli to actually talk about it this spring. So this is Riemann, one photograph of him. I think the only photograph of him without glasses. And his grave doesn't exist, but the gravestone is in the wall of the cemetery in Salaska where he was buried. And so this gives the dates and so forth of his life. I don't think I need to go into that in any more detail, but it's so this is for those of you who are interested in this sort of thing. This is where Riemann lived, roughly speaking, at the time that he discovered the Riemann hypothesis. And so this is the 1854 to 1857, the sign is there. And if you look up the road here, this is the aula of the Goettingen University. It was opened in 1837. It is almost certainly where Riemann held a talk on the origins of geometry. So you have everything in a very small compass here. And after I decided to give this talk, there has been more material becoming available. I want to point out two of these, which I will come back to in due course. One is a book published by de Gruyter, which is the correspondence between Weber and Dedekind, which is absolutely fascinating. Unfortunately, the book is expensive and completely in German, so that it probably is not reaching a very large audience, but it is a very well worth studying. And then this year, 2016, new letters from Riemann to Wilhelm Weber have been discovered in the Smithsonian Museum by Juan Marin, and then they were transcribed and have just been published about 2 weeks ago by Wolfgang Gabke, and they are in the archive at the moment. One of these I will show you later on. So the material that has become available has been expanding as I've been preparing this, and it has been opening up new possibilities. But I reckon I'd better get the business with rainbows and pots of gold and so forth out of the thing pretty quickly. So there will be very little about the Rosita function immediately in this. But this is a rainbow, the coloration, and you can see inside here there's another rainbow. This is what's known as a supernumerary rainbow. And what happens is the following. is that whenever the water drops are falling, Descartes showed that there is this particular angle, 53 degrees or whatever it is, so the light reflects round. And if you take slight variations of this, there is the path varies a little bit, but it's a third order difference that occurs. And the difference is if your raindrop is a millimeter or a bit under a millimeter, is in these path lengths is of the order of magnitude of the wavelengths of light. So you get phenomena which arise because of the wave nature of light. And this was analysed by Airy in 1838, and it was studied. I mean, the colours of the rainbow haven't come out very well here, but this is one of these rainbows which shows that the particulate theory of light is not adequate. And the irony of this is Newton's, the house where Newton was born. So this rainbow is disproving Newton's theory of light. And the integral that actually describes this is the Airy function, which comes in slightly different normalizations, but we can take this normalization here. It's an improper integral. It's quite difficult to compute, and its behavior depends on whether z is positive or negative. If we go back to this, you will observe that in this area here, the sky is very dark. Here it's bright, and this is actually reflected by z going from positive to negative in the integral. And so this integral became quite an important issue in optics. I mean, it's been studied by lots of people since then, but it was especially studied by George Gabriel Stokes, who was the professor of, the Lucasian professor in Cambridge for the whole of the second half of the 19th century, from I think 1848 or 1849 to 1903. And he wrote a paper in 1850, which was in the Transactions of the Cambridge Philosophical Society, which I should point out was available in Goettingen. And Riemann almost certainly read this because he read other papers that are related to this when he was working on the theory of sound. And he discusses this integral, and he says that Airy had enormous difficulty in computing it because it's an improper integral. And he then says, after many trials, I at last succeeded in putting Mr. Airy's integral in a form from which its numerical value can be calculated with extreme facility. Moreover, the form of the points out without any numerical calculation the law of the progress of the function when m is large. It is very easy to deduce from this expression a formula which gives the ith root of the equation w is equal to 0 with hardly any numerical calculation. So this was actually going to be what Riemann took up whenever he was studying the Riemann zeta function, and it seems to be quite clear that he studied this and then he developed the ideas, developed them a lot further, but he started from Stokes' ideas in order to study the Riemann zeta function. This makes it clear why he took on the strategy that he did. So this is a very important paper. Most of you will be aware that Stokes' theorem was actually a theorem which was sort of sent as by Lord Kelvin, or Sir William Thomson as he then was, to Stokes as an examination question for Cambridge. In this paper, there is the opposite thing, where the Kelvin's principle of least of stationary phase is actually used in this paper 35 years actually before Kelvin actually published it. So they're quite...
We should add that examination, the only person who answered the question correctly was supposed to be James Clerk Maxwell.
Aha.
Exactly. He gave the first proof of Stokes in the examination paper.
Yes, but there is one story going around, I don't want to get to, that the goal of Goettingen was to give a complete proof of Stokes' theorem and never finished this. Whoops, sorry. No, what is happening is that the Riemann zeta function, I'm not going to introduce the Riemann zeta function directly here, but I want to point out one or two things that are associated with this. If you, there is a formula due to Euler for the sine function, which gives it as an infinite product. If you differentiate it logarithmically, you get this particular expression, and from this you can derive basically the theory of Bernoulli functions, Bernoulli polynomials, and the like, from which one can, there's one approach to Fourier theory. So what is going to happen is that Riemann is developing a kind of Fourier theory for the prime numbers. This is what the Riemann zeta function is about, and this is the model that he is using. And the fundamental formula that one uses is this particular function here. This is an interesting function in its own right. And this is the first Bernoulli polynomial here. And it is this Fourier expansion. And from this, one can actually deduce much of Fourier theory and a great deal besides. Incidentally, this was the function that which Cauchy's theorem of Cauchy's would have claimed was continuous, because the right-hand side converges everywhere, but for different reasons at 0 and not at 0. And the left-hand side is discontinuous, and it led Stokes, amongst other people, to the discovery of uniform convergence. So, the ideas that were used by this function can also be used for Bessel functions, and Riemann was actually very interested in Bessel functions, so that he this is where he started in studying the Riemann zeta function. And he began to study the questions about prime numbers were very much in the air around about 1848. There were papers of Chebyshev's which had actually not appeared in the West by this point. They appeared first in about 1852, which was before Riemann's paper appeared, but after some other one. But there was another paper. There were another paper, or two papers in fact, by a lawyer. Wolfgang Gabke, who I mentioned before, is a retired teacher. Hargreave, who was responsible for actually using some of the ideas with the Riemann zeta function, first of all, was a London lawyer who later became a Dublin lawyer. And he actually published in one of the philosophical magazine, which was also available in Goettingen, work which was not quite as good as Chebyshev's, but going in the same general direction. So Riemann had mastered complex function theory to an enormous extent by this point. I mean, what this one knows, he was able to go much further than anyone else. And what he was able to do was to get a summation formula for the prime numbers, which reflects the prime numbers in terms of the zeros of the Riemann zeta function. That is in itself, wasn't that sort of the end of the story. But what he did do was he was able to compute these zeros, and he was able to compute them to some extent, so that he made this notorious assertion that the number of zeros was more or less the same as the total number of zeros. and came to the Riemann hypothesis from there. So this is what happens. Riemann was the first person to use the principle of the argument in this context, which he was very, very adept at. And he used he found a very nice representation for the number of zeros. He had to use, it was all relatively sort of mathematics which, if you know the right place to look, was available at the time, but it wasn't generally available. So the information you need about the gamma function was available from a very long memoir of Binet from 1839. And Riemann did the computations, basically using developments of Stokes' ideas, very substantial developments, but he did not actually have a rigorous foundation for the computations. These only were developed by people like Backlund and others good 50 years later. But other people did do computations of the zeros in the intervening period. Now, in the one of the things that sort of strikes one is that in all of this, the model of Bessel functions, which is, I'm probably going to be the only person in the whole history of the Topology Seminar to talk about Bessel functions.
I think that's correct.
Yeah. This was usually what people like Christopher Sieben were doing their best to avoid when they went to Warwick.
book on Bessel functions was given to me by my maths teacher at school as a party present.
Yes, well, it's a wonderful book. There is a theorem which is actually due to Fourier, which actually claims that all of the zeros of J0, the Bessel function J0, are actually sort of real. So this is actually the analog of the Riemann hypothesis for this function. Hurwitz cleaned the proof up. It uses an approximation to the Riemann zeta function, to the Bessel functions by rational functions, which one uses the differential equation in order to find. There's a second proof which Watson attributes this to Eugen von Lommel, who had nothing to do with Riemann whatsoever, but is also given in Riemann's lecture courses on applied mathematics, and it uses an integral equation that the Bessel functions satisfy. And so there were two proofs, and a lot of people in the intervening period, especially to George Poyer in the 1920s, attempted to use these techniques of Bessel functions in order to prove the Riemann hypothesis. One can actually say that you can see who was trying to prove the Riemann hypothesis by a trail of theorems about Bessel functions. This was something that, having said all of this, this is sort of for background information. When I'm going to talk about this in Belfast, I mean, this is what I've just said is not what I'm going to talk about, because this is clearly for a mathematical audience. And but what one has a problem of, and this is where acoustics comes in, is how do you explain Fourier theory to a general audience? And so this is the bit which I'm going to be talking about here. Marcus Suzatoy called his book and his TV program Music of the Primes, but there's very little about music in it. And actually The program, he goes around waving his trumpet in the air at various points. And Chris Reed was the guitarist. He also didn't have anything to say about music, but let us go on. So just to get an idea, this is the counting function for the prime numbers going up here. And this is a nice smooth function. It's not quite the usual function, which is the integral from 2 up to x of dx over log x, the logarithmic function, logarithmic integral. This is a slight approximation to that, which was slightly easier for me to compute when I was doing it. And when you sort of go up, whoops.
What's being counted?
Huh?
Can you explain what is the prime interpretation of LIX?
No, this is a nice smooth function.
Yes.
So the blue line is this function here.
Yes.
The other one counts the number of primes. It's usually
okay.
described as pi of x, and it's the number of primes less than or equal to x. Okay, so and so it's a step function. You can see this sort of up to the resolution, going up. They are quite far apart here, but as you go up further, they get closer and closer. So the scale, this is going up. This was as far as I went, which is I think it was sort of 4 million that I took the calculations up to, so that at this point you can't actually visually see a difference anymore in these. And the question is to try and understand this difference. This was the first approximation. In fact, during the 19th century, people were very dissatisfied with this as an approximation. It was put forward by Gauss, it was put forward by Hargreave, and it was put forward by Chebyshev as the good approximation. But others later on, especially Gleicher, were thoroughly dissatisfied with it. So, now to explain something about the sort of Fourier theory, so you can tell me whether I will get away with this whenever I'm sort of speaking in 3 weeks' time. So this is a little ditty from Belfast, which which sort of the girls at school used to sing when they were skipping. So what I want to point out here is if you think horizontally here along these lines, you have the sounds of the music. If you think vertically in terms of the notes, you're dealing with the Fourier analysis of the music. So you're saying exactly sort of which notes are sort of being played here. And this is, so in a sense, the first case where you actually meet some kind of Fourier analysis is in musical notation. We know that the ear in the cochlea actually does a Fourier analysis of the sounds coming in. I'm not going to get involved in this. We will come back to it later though. So this is now in order to, you can take this much further for the people from the acoustics here. I'm telling them what they're doing every day. So, but I want to explain the Fourier analysis through sonograms, which are only a partial explanation, because really what we're dealing with here are wavelets rather than a proper Fourier analysis in the traditional sense. But this gives the closest analogy to which I could find for a general audience, and then you can see things like this. However, this is I've been using a program called WASP, which is developed by the University College London, And it is really quite nice. I mean, I was supposed to, there was, the computer reacted rather too slowly there, and I missed this. But there are two voices here, sort of a male voice and a female voice. And what you see here is the lowest, it's actually the frequency with which the larynx is vibrating. And the sound that we hear is put together through a whole series of overtones, which you can see very clearly on this. In many sonograms, ones which are put around, for example, for playing music and the like, you cannot see this structure at all. So this gives the basis of this. So the bits that we actually really listen to are much more up here. What you can see is the difference between the male and the female voices moving from here to the somewhat higher frequencies here. And one can read off a great deal about the actual formation of these things. I should perhaps add here that quite recently there have been wonderful MRTs made, some of them in Goettingen, of the people singing in an MRT, singing their hearts out, and you can watch this in real time now.
What is an MRT?
Magnetoresonance tomogram.
I see.
So you can actually see the inside of their vocal tract while they're actually singing, and it really is quite dramatic to see. The only way that I could have done this was with an internet connection at the moment, and I wasn't going to risk that. I mean, this was going too far, but they're absolutely dramatic. So you can see how these things are coming about. But in this, you can see the frequency structure here and the time structure, and the two voices going together. So this is a singing voice, which is by a singer who is not a professional singer, called Albert Fry. I think he's actually an engineer in Belfast, and he plays the guitar. So you can see the guitar along here. It's a love song, in fact, in Gaelic. And then he sets in, and you can see the vibrato here that is actually coming in, and how this is controlled. It's quite a different structure that appears whenever one is dealing with this. Now, it might or may not play this. Chances. It's only a few bars, so yeah. Okay. Well, this is it being played, but the sound is not coming through, so
Chris, can you try to turn it on?
it is plugged in. I mean,
Thank you.
Oh, mute. Okay, good. Let me go back and see if I can do this again. Okay. Interesting. Because I thought this might be one bridge too far. Okay, good. So this is something that one actually has to try out in advance. So this gives some idea of what voices sound like. Music itself looks rather different, so but you can see how the notes here sort of match up, but there's an enormously complicated overtone structure in each of these. The correspondence you might think ought to be linear, but the length of a printed bar depends on the printer, not on the time, so that it looks rather like this. So you get a very sort of structure like. Now, when I began to do this talk, I thought that I would explain how musical notation actually represents Fourier analysis by talking about how the musicians record birdsong. And I thought this would be an excellent example of how you can do some acoustics that you meet in the real world. And I started work on this, and I discovered a lot for myself from this, which was sort of rather sobering. So this is from the German Encyclopedia Brockhaus. It's supposed to be the Great Tit, a recording of it. This would be about 1500 hertz, so we'll be up somewhere about here. You can see actually that the actual sound is quite different. The syrinx, the sound box of the birds, is a vibrating membrane, sort of roughly where the windpipe sort of splits, and it vibrates and it does not produce overtones. So you get a quite different sound, and it's very short bursts, so that this is actually miles away from an accurate representation. But this was an attempt by somebody who was scientifically minded to represent birdsong. But this is trying to show how birdsong actually looks whenever you sort of represent it on a sonogram, and what it looks like otherwise. You might have ended up getting sort of a dose of birdsong if I got the technology sorted out. So you might say, well, you're Ludwig van Beethoven had a sort of an ear like nobody else, so there is a cuckoo sound here, and this is actually a cuckoo here. A cuckoo here. You'll excuse me getting mixed between German and English. And he gives this. So what you see here is that actually the sound of the cuckoo goes up and down. If you listen to it, which you're unfortunately not able to do, you can hear this actually quite clearly. Beethoven doesn't manage this at all. The length of the two parts of the song, or if you can call it that, of a cuckoo, are about half the length that he is giving here. So this is a metronome marking of 130. And the notes here are, the notes that Beethoven gives are far too low in terms of what you can measure here. So even a great musician like Beethoven does not give an accurate representation. Beethoven, of course, was producing music. He was not being a scientist, and so
wasn't he deaf by the time he wrote the pastoral?
No, he was. This is actually, but it's supposed to give a mood, and it's not supposed to be an accurate representation. Messiaen, who I was going to go into, and then decided that it was on an absolute minefield, went out in the mornings in his willies and in the swamps, and actually tried to record birdsong, and they also go a long way from what you get from a sonogram. Okay, good. So we're now going. This is a red herring. Having said a little bit about this, I'm going off onto something slightly different, but which is related to this in a slightly contorted way. I mentioned earlier on that there were new letters which were put together by Wolfgang Gabke. They were discovered in the Smithsonian, and exactly how they got there, they are not actually formally addressed to Wilhelm Weber, but it seems to be close. This is a letter which was written on the 18th of April 1866. So this is a letter which is written not in Riemann's own hand, but in the hand of his wife, Elisa. And unfortunately, we know very little about her. There's not a single photograph of her in existence, as far as I know. And but she seems to have actually, when you study the correspondence between Goettingen and Weber, you discover that she actually knew very well what her Bernard was up to most of the time. And she was quite clearly a very helpful person for him. Wolfgang Gabke says that this was in Elisa's writing because this was 3 or 4 months before Riemann died, 3 months before he died, and he was so ill that he couldn't sort of lift a pen. I don't buy this because of the content of this letter, which I will come to in a second. And Riemann did sort of manage the journey to Salaska in July 1866. It took him 3 weeks to get there, and he died 3 weeks later, and the journey seemed to have finished him off. He was, like so many people nowadays, fleeing from war. So this is the of Wolfgang Gabke's consideration of this. So I was sort of slightly, this is sort of a bit mixed up here in the course of but what Riemann is actually writing about, and this has to do with what I've just been talking about, is that he is writing to Weber in order to get Weber's nephew to send him scalpels and saws for cutting bones. Riemann was interested in the physiology of the ear, and he was making well, probably quite literally a dog's breakfast of the whole business, but he was getting heads of presumably pigs and perhaps cattle from the local abattoir in Goettingen, and was cutting them up. I don't know what Elisa thought of this, it's not recorded. He was trying to get at the ear in order to make measurements of the ear, and he was finding that the bones around the ear were so hard that he wasn't able to get through them, and so he is asking for the equipment in order to be able to cut the bone to get into the parts of the ear much more easily. I mean, it would have probably been a complete waste of time because I take it that cows' ears or pigs' ears are fundamentally sort of different in this respect to human ears, which is what he was really interested in. But when Andrew sort of describes his work as surgery, Riemann was really hands-on. Not all over the place.
What's a Riemann?
Yes, yes. So this is one of these letters that actually changes one's whole view of Riemann. I think if Riemann had actually grown older, he would have been somebody like Helmholtz rather than another Weierstrass. and he was really trying to get at the ear, measure it, and his manuscript on the mechanisms of hearing were left unfinished at his death. My view about this letter is that it shows that he wasn't lying sort of totally weakened on his sick bed at the time that he wrote this, because you don't go cutting up this sort of thing whenever you're sort of at death's door. And Riemann was clearly in a state whenever that he could actually do this. So for some reason he had asked his wife to write this letter for him. I mean, perhaps it was simply the fair copy, but he does sign it himself. The signature at the end is by him. So this is the rest of it. Yes. So this is the Klein. It actually is written at K-L-A-I-N-E, Sig, and so forth. And he's asking here for the nephew to send this, and he wants to do the exact measurements. So, as I say, 3 months before he died. No. This is certainly when I saw this, and this transliteration has only been around for less than a month now. It's changed my view of Riemann. Yeah. I mean, it's considerably. So I wanted to at least show you this. And so this is Wilhelm Weber and his two brothers, who were both professors of one of anatomy, the other of physiology in Leipzig. And so there was a direct connection. This is one of the things that speaks most strongly for Riemann having for the letters actually being written to Wilhelm Weber. So I suppose I ought to give people are sort of decided it's 5 o'clock, and those who wish to sort of go up, I suppose, should do so. Make a small break for those who have to do so at the moment. And
Can I ask a question? Did you contact any current anatomists to see whether things have moved on since 1866?
Well, I mean, well, there's very good sort of pictures of the cochlea and so forth nowadays. I mean, and biomedicine. I mean, you have John Murray, for example, here, and people like this who are.
But did they confirm what Riemann was?
Well, Riemann couldn't get in. I mean,
He had no theory. I mean, he had no theory.
He wanted to have a numerical theory.
Oh, I see. He didn't have.
He couldn't get this, and he was talking here that he could have got a possible help from an anatomist in Goettingen, but he wanted a sort of fresh ear so that he could measure these things properly. The dried out ones that the anatomists were using were not suitable for him.
I see. Got it.
So it was something that was no. When you read this about Riemann, then one is reminded of Listing. So Listing invented, wrote the first book, proper book on topology, the Vorstudien zur Topologie, in 1848. 2 years before that, he invented ophthalmology in a book called Physiologische Optik. And he was a sort of a remarkable character, and there is a biography of him written by a guy called Otto Schwarz, which seems to have eluded people. One thing I felt that it doesn't seem to be known, even in St. Andrews, is that his parents died, and then he was taken it was taken in by a Frankfurter patrician family, Bernus MacGregor. So there is a Scottish connection here. I take it that this was a Jacobite family which had moved to Frankfurt, probably either after 1715 or 1745. And one of Listing's great fans was Tate. But Tate says that he had learned about Listing from Maxwell. So it seems that Listing, although he wasn't read by a huge number of people, was read by Bernard Riemann, James Clerk Maxwell, and Peter Guthrie Tate. So not bad. And this is he also worked on volcanoes. When Riemann was a student in Goettingen, he was lecturing on steam engines. I don't do this sort of thing anymore. And then this comes to an end in that he died in an accident. There is a vast amount of papers of him in Goettingen, which nobody has looked at. Tate says that he hopes that somebody will work through the papers. None of the historians have gone about this at all in Goettingen, and this is Otto Schwarz here is going on about that this should be done. So this was in the 1905 or so that this was written, and yeah. Okay. So the next thing to do, there's going to be a bit of a disaster here because the sorry, we will go on. Yeah. So I've talked about up to the present about sort of sounds that were sort of controlled voices, birdsong and so forth. So the sonogram that I've just shown you shows this, and it shows a great deal of spectral sounds going much higher than sort of up to the top level, about 8,000. And this is a quiet river, so that the main sounds are really quite low. For some reason they remain in sort of fairly strong bounds. So you get now a picture of a nice brook, which you imagine the sounds. You have to fill this in. The next one that's going to be even more difficult is that
I think this is the Tarkovsky moment of the lecture.
sorry?
Which?
This is the Tarkovsky moment of the lecture.
Andrei Tarkovsky.
Yeah.
Yes.
Russian filmmaker.
Yes. These, I should say, so I filmed myself so that there is no copyright of any sort on them. The Riemann is sort of hypothesis, as I've said before, is a matter of resolving things into frequencies. And the Riemann hypothesis, which is the way that I'm trying to explain it to a general audience, is saying that the sound of the primes is much more like a murmuring brook than it is like a rush of a waterfall. And unfortunately, you will now be. So this is this is what it looks like if you don't remove. This is the bias that you saw there, but the real sound is up here, and you can play this, and oh, this is Tom Apostle singing, which you also can't hear, but which I sort of I think I must do this one sort of independently. This is Tom Apostle's book on mathematical analysis was the first book on university mathematics that I read.
Me too, actually.
Yes, this is him doing this. So I will do this again and try and do it directly, and see if we can do it a little more successfully.
Oh, where are the zeros of zeta of S? GFB Riemann has made a good guess. They're all on the critical line, stated he, and their densities 1 over 2 pi log t.
So, okay.
Sounds like Tom Lehrer.
Yes, I think it's very much under the influence of
Yes.
Tom Lehrer. I think they've been slightly wittier to Tom Lehrer.
Well, the sound,
Yes.
Now, I want to finish with a sort of a talk that I gave in 1987, where I was talking about a different type of zeta function, a so-called Selberg zeta function. Selberg was in the audience, but I made a couple of comments about the Riemann zeta function, and I said that the Riemann zeta function essentially says that we're living in, as far as the prime numbers are concerned, we are living in the best of all possible worlds. And Selberg came up to me afterwards, and he said, you know, this is referring to Leibniz's theology, it is very clear that as far as the real world is concerned, we are not living in the best of all possible worlds. But, he said, in things that really matter, like the Riemann hypothesis, he was convinced that we were living in the best of all possible worlds. So that I will leave it at that for the moment. Okay, thank you.
Very much.
I will now try